So in this example, we're given a position function. So it's expressed as height. The height of an object t seconds after is dropped from 120 meters in the air is given by this function s of t. So again, think of this as our position function, negative 4.9 t squared plus 120. First part of this question is having us calculate the average velocity. So that's our average rate of change during the first 3 seconds. So that's going to be over the interval from 0 to 3. That's the first 3 seconds. So part A, finding that average velocity, we want the final position, which is going to be the position after it's fallen for 3 seconds. Here, just imagine, you're dropping something off a building. So you've got this position when t equals 3 seconds. And then this position up here when t equals 0, which we know that position actually, it's at a height of 120 meters. Notice that is what you get when you plug 0 in for t into our position function here. But so this is our final position minus our initial position. That'll give us our change in position. So that'll be s of 3 minus s of 0 divided by change in time, which is 3 seconds. If I follow that f of b minus f of a over b minus a format, I'll be writing 3 minus 0 on the bottom, but it also just makes sense. Yeah, the change in time is 3 seconds. Okay, and s of 0, like I just pointed out, our initial height is 120. So that makes both, makes sense in general just by reading the problem, but also if you substitute 0 into this function, you'll have negative 4.9 times 0 plus 120. S of 3 will be negative 4.9 times 3 squared. So that's 9 plus 120. And so I'm actually going to grab a calculator. Let's see. So that's 75.9. So our final position is 75.9 meters minus initial position. So the change in position is negative 44.1 meters over the 3 seconds for our change in time. And I mean, part of me wants to just leave it like that. I guess I'll go ahead and get a decimal approximation. So that's negative 14.7. Well, and that's not even an approximation, is it? That's exact. Negative 14.7 meters per second. So there's your average velocity during the first 3 seconds. Part B is asking us to find the time during the first 3 seconds. If that's our average velocity as the object falls for the first 3 seconds, then that's mean value theorem tells us then at some time during those first 3 seconds, the object was falling at exactly negative 14.7 meters per second. The instantaneous velocity must be equal to the average velocity at some point in that interval. And so we're supposed to find out when that happens. So instantaneous velocity is given by the first derivative of the position function. So that'll be negative 4.9 times, if you differentiate t squared, that'll be 2t to the first, plus the derivative of a constant is 0. So we end up with negative 9.8 t. So this is our velocity. Instantaneous velocity is given by that expression. So now just set that equal to the average velocity, negative 14.7, and then solve for t. So we can just divide by negative 9.8 on both sides. And that gives us 1.5. So t is equal to 1.5 seconds. So right in the middle, exactly in the middle of that time interval is when this object's instantaneous velocity is equal to the average velocity.